So I'm Jean-Sébastien Bevilacqua. I work at Linagora. It's a French company that you may know that promotes free software, and it's this company which encourages me to give this talk today. So if I give this talk, it's because I truly believe in CFFI to improve maintainability and robustness of Python extension. I want to share with you my experience in order to convince you to give a try to CFFI next time you build a Python extension. So, first, why do we need Python extension? Well, we know why now. I'm going to tell you my use case. So approximately 1 year ago, the new Vulkan API was released. Do you know Vulkan? It's a graphic API. I think you know, maybe, no? So that follow OpenGL. No? Okay. So it's a new graphic API that will replace OpenGL. So back at this time, I was enjoying OpenGL development, but with Vulkan, I saw an opportunity to improve my 3D knowledge and to improve my knowledge in 3D. Because Vulkan is very close to the bare metal compared to OpenGL. So at this time, Python was my language of choice. We all know why. But there was no binding between Python and Vulkan. As you may know, Vulkan is a low-level API, and in order to use it, you have to call low-level functions like dlsym or dlopen. So I decided to write my Vulkan binding for Python directly in C with the CPython C API. You should know that Python extension can be used to improve performance too, but that was not my use case. Sadly, with C language, you have a system error like segmentation fault. With Python, it can be very hard to track a segmentation fault, like we saw just before with Jean-Baptiste. So Valgrind can help us, but it's still a difficult task. To write a Python extension in C, you have to make use of the CPython API. It allows you to create a module, add functions and classes in it. After reading the very good CPython API, I started my C extension, so it was clear and I felt self-confident, but it's still C. We have to fight against malloc and free like usual, but because it's too easy, CPython API adds the reference counting and the cumbersome API. You can confirm. I almost gave up several times due to the amount of work. So we are going to see existing solution to resolve the complexity of C extension. But before, let's see ABI and API mode, because I will use always this term after. So API means Application Programming Interface, and ABI, Application Binary Interface. So you have to understand the difference between the two. The API mode is what humans use. When you call a function, you need to know the name of the function and argument to pass. So as a programming interface, it's all expressed in source code. The ABI is very similar. Think of it as a compiled version of the API. To be clear, when you write the program, you use the human API. Then, when your program is compiled, computer will access the ABI of the library. Maybe you wonder the goal of the ABI from a human point of view. We could just stick to the usual API mode. Accessing a library with ABI mode allows you to dynamically link at runtime, and thus can be used with an interpreted language without compilation, like Python, for example. So you have to really understand the difference between the two. It's a tricky part needed to fully exploit CFFI potential. So let's see the existing solutions to easily write a Python extension. Like I said just before, you can do it with the CPython API, but it's a difficult task. So the first one is Cython. The boss people before me just talk about Cython, so I don't need to present it, but Cython is an interesting approach. It can execute directly your Python code, and you can add new syntaxes elements by iteration. So it's very good, but when you start to add custom Cython syntax, your Python code is no more Python. And so you lose portability, and Cython becomes a required dependency. You should take that into account before using it, because such a high dependency can be dangerous. So Cython can be compiled and thus supports ABI and API mode. Now let's talk about CTYPES. CTYPES is a built-in. It's a good solution because we can be always sure CTYPES is always available. With CTYPE, you don't need compilations. It works only on the ABI level, not on the API. So you dynamically link at runtime to your library. But like you can see on screen, to use CTYPES, you have to learn a new API. Like you can see on the screen, you have to translate your C header to the CTYPES API. In this example, I declare a point struct here, and get back the vector size function here from the library. So it's error-prone and cumbersome. You can have a segmentation fault with this way of writing an extension. Now CFFI, it's beautiful. 7 years ago, two smart people, Armin Rigo and Maciej Ficzarkowski, created CFFI. You may know these names because they authored PyPy too. PyPy, not PyP. It's not a piece of cake. For information, PyPy is an alternative Python interpreter with a JIT. JIT means just in time. At first, CFFI was an alternative to CTYPES. It was working only on the ABI mode. Later, the API mode was added and revolutionized the Python extensions ecosystem. Before CFFI, to create an API mode extension for Python, you had to use the CPython API or Cython, which only work with CPython. With CFFI, extensions are working with CPython 2, 3, and PyPy without changing one line of your code. Now you understand ABI and API mode, I can show you how it works with CFFI. But let's introduce another concept of CFFI. This one is a lot simpler than ABI and API mode. In the inline mode, everything is set up every time you import your Python code. In the out-of-line mode, you have a separate step of preparation and sometimes compilation that produce a module which your main program can then import. Of course, inline mode only work with the API mode, since API, inline mode only work with ABI, because API mode always require compilation. Sorry. So, this first example shows how to work with ABI and inline mode. So this is the first feature supported by CFFI, and it's exactly what CTYPES is done for. Do you see what? Yes, okay, it's good enough. Like you can see with CFFI, you just pass the C header to CDEF and open your library. That's all. Do you see the difference because CTYPES? With CTYPES, we have to define the struct with the CTYPES API. Here, we just copy-paste the C header. One line here. So it's magic. It's why I love CFFI. It's clean, intuitive, so go for it. Now, a small demo, okay. Just a small demo of the ABI mode. On your right, you have the code, and I will. We don't see the left part. Sorry. Okay. Is it working? Okay, yes. Okay, it's at bottom. So on the right, you have the code in demo1.py that I will execute. So I just loading the entire C namespace with DL open, and I tell CFFI that there is a printf function in it. I use IPDB to stop the execution of the code. With Python demo1. Demo1, okay. Okay, so we are here at the line import IPDB. I will printf with the C printf function. It's difficult. Okay. So here you can see that the printf function prints test, like I asked her. The number under, it's the return code of the function print. It's not the output. So this is not the print function of Python. It's the printf function of the same namespace in just one line. Now we are going to see the API mode. So CFFI goes one step further with its API mode. Syntax still similar, but you can notice a difference. We pass C code to CFFI with third source function. Then you just ask CFFI to compile here your module. Your Python extension is robust, fast, and easy to maintain. With this API mode, you can't have segmentation fault due to a mismatching API. You can have segmentation fault if you have segmentation fault in your C code, but not because of the mismatching API. Moreover, it adds a convenient feature here. You can replace useless value by 3 dots, but I will not go into detail on these features. So let's see running. The API mode now. Yeah, demo 2. So on your right you see the code. Okay. Yes, okay. I compile my module. Ah, okay. Thank you. It's good like that? Yeah. Okay. Okay, so like you can see, the CFFI automatically calls the GCC compiler for us. Here you can see GCC. What CFFI does, it generates a C file. If I do ls, you will see. So it generates the C file demo2.c, and it gives this C file to the compiler to create the Python extension. So if you take a look at the source code on your right, we just include pwd here. And in the CDF, we don't need to add all pwd functions, just the one we want, the both one here. Let's try. I want to know what is my UID, for example. So I have a cheat here, but I can't see. So okay. No. Yes. So I can't see, so I will not do the demo here, but you can trust me, it works. Okay. Now the interesting part. So I'm currently building a 3D engine with Python and the new Vulkan graphic API. So like I said to you, I created a Vulkan wrapper directly in C. But if I'm here today, it's thanks to Armin Rigaud, the creator of CFFI. When I show him my Vulkan wrapper on IRC, it tells me, such a shame you didn't use CFFI. He then explains me advantages of CFFI. It took no more to meet a new challenge. Write a Vulkan wrapper directly with CFFI. So was I ready to lose months of work? It's a hard decision, but I definitely made the right choice. I'm going to show you why. So like all engineers, we love statistics. Vulkan API is huge. 100 of functions, 100 of structs, 100 of constants. More than 5,000 lines of code just for the C header. So wrapping all this API in plain C is just madness, as you can see with this number. It's just line of code without space. More than 62,000 lines for the generated C file. So I'm crazy enough to have done it, but it's a good experience. Whereas with CFFI, it's only simple and clean Python code. To give you an idea about times, it took me 1 month and a half for the C version and only 2 weeks with CFFI. This time is only on my spare time, so it would have taken only 1 week at full time, I think. And when I got an open issue on GitHub, I can fix it in 1 hour usually, because it's just Python. The C version was too difficult to maintain. How it works now, how this wrapper is done. In both cases, I use a generator. So Kronos Group, the group behind Vulkan and OpenGL, did a great job with Vulkan. All is open source, and you can contribute easily on GitHub. It provides an XML file that describes the API. So my generator takes this XML file as input and generates the Vulkan wrapper as output. By doing a generator, I can update the wrapper in 2 minutes when a new version of the API is released. Basically, here's the steps. So first we load and parse XML definition. Next I generate the data model. And finally, I generate Python model with the Jinja 2 template system. Maybe you know Jinja 2, yes. So parsing is done with XML2Dict. It's a module, it's a good way to parse an XML file without DH. It transforms your XML dict into a hierarchical dictionary. So now that we have a good data model easy to parse, we can pass it to the Jinja 2 template. And that's where the two modules differs. What you see is the folder structure of the C extension. For the C extension, there are too much things involved. To keep code maintainable, I had to split it up. Line of code is a good indicator here, but what is more important is the complexity of the code. Like you can see, it's pretty huge. Moreover, with C code, you have to manage memory yourself, and this is error-prone. Now with CFFI, despite of its looks, what you see on screen means a lot. With CFFI, I didn't think about architecture. It was obvious. All in was in one file. One more point for CFFI. But you don't have to trust my words when I say CFFI is better. Let's see it in action, and you will understand. So constant is the easier part, and both cases are simple. In C, we just use the CPython API to add constant to our module, but we had to take care about the type of the constant. With CFFI, it's just Python, and it's dynamically typed variable. So we don't care about the type. Object not. Only with constant, you don't go far away. Next step is to create binding for struct. But there is no struct concept in Python. There are objects, which is similar. So with CPython, you have to handle the new, delete, init, and get for each member. You have to use malloc to allocate memory to your objects in new, In del, you must free your object. In init, you have to pass each parameter with CPython utils function. And in get, you have to convert C strict to Python object. I can assure you it takes a lot of time to figure out how to do it properly. Code is so long that I can't show you an example on screen. Now with CFFI, it's 40 lines. CFFI handles for object allocation and deletion. I just use plain Python to handle all strict initialization in a generic way. I repeat to be sure you understand, this generic new function works for all strict of the Vulkan API. With CPython API, the step I showed you just before must be done for each strict, and there are hundreds of strict. When you realize this benefit, you just fall in love about CFFI. So what I showed you until here is the API mode. Let's try the fast and robust API mode now. We are going to wrap another library with the API out-of-line mode. This mode is robust and fast, but you need compilation. The library we are going to wrap is ShaderC. ShaderC is a free software done by Google guys and give you the ability to compile GLSL to SPIR-V binary. GLSL and SPIR-V formats are used to create programs for your graphic card. So I usually create a folder dedicated to CFFI named CFFI build here. And I recommend you to do so to keep a clean separation of concerns. ShaderC.h contains function signatures and structs of ShaderC. Hopefully, Google have done a C header for us because it's C++ behind. So we just copy-paste the header provided by Google, and CFFI handles it. PyShaderC build here is used to generate the Python extension. Next, we have the PyShaderC folder here containing our wrapper. And finally, we'll take a look at the setup file with a special CFFI feature. Like you can see, we first read content here of the ShaderC header and pass it to the cdef function. That's all for the definition. 3 lines, and CFFI knows how to handle this library. It's beautiful. Okay. Now with the building part. With these few lines, we tell CFFI to compile the source here with statically linked library ShaderC combine this library. And to name the extension PyShaderC, the first argument of seed source is the name of the extension. So ShaderC combine is a statical library that we have to compile before running this CFFI parts. I don't show you how because it's not related to CFFI. But you can go on my GitHub and you will see. So, like you can see, there is no C involved. We just tell CFFI to open a Python portal to the ShaderC library. Here again, it's simple. Use. Currently, our extension is ready, but we remain dependent of CFFI. For example, if you want to pass a pointer to a function, you have to use CFFI. When using your wrapper, your user shouldn't need to know CFFI, it's just a dependency. So we are going to write a small Python code, especially for that. This code is located in the init and is loaded automatically when you import your module. So first we load our extension that we have named PyShaderC, which contain IFFI and lib modules. Lib contains all functions and strict related to our library. So we need FFI too to interface with our lib. So let's examine the compile into SPIR-V function, because like I said, ShaderC converts GLSL to SPIR-V. So all functions defined in our extension can be accessed through lib. Here, lib and lib. If you take a look at the compile line, the last line, okay, we can pass pure Python types like int. Here it's a int, and here it's a string directly, and CFFI converts it for us. It's clean and intuitive. Note that with Python 3, here we have to pass a bytes, not a strings. Next, shall.c returns a pointer to us. We have to tell CFFI to convert it to a bytes Python object. So we first get back the pointer here and the length. But we can't directly copy the data to a bytes Python object because bytes types is immutable in Python. So we have to copy data into a byte array. Here, I copy data into a byte array with these two lines. And then we pass it to our bytes object here. Take a look at the CFFI.memMove functions. It's similar to the memcopy function in C, but directly in Python. So I'm doing memory manipulation directly in Python with CFFI.memMove. In bonus, CFFI provides the setup tools integration. Just add the entry CFFI modules here, and your extension will be built by setup tools when you will call Python setup.py install or build. Now a small demo of the results. So we have two wrappers, PyShaderC and Vulkan. Let's play a simple game. Okay, let's go on my screen. Okay, so it's not very impressive, huh? But this game is working with the new shiny Vulkan API released just 1 year ago, and you don't see, but there is a program directly sent to your graphic card, compiled to SPIR-V. So it's not impressive, but now we can do something impressive. It will take some time, maybe for my next talk. So I hope that, like me, you enjoyed this talk. If one day you need to use a C library or to improve performance of your code, think about CFFI, please. So thank you for your attention.